I thought we should look at the working of a gasoline engine. And the idea of the gasoline engine comes from Carnot's engine. We'll look at the basic functioning of the Carnot engine and then transition to the practical gasoline engine. So here we are. A Carnot's engine must have three parts. It should have a source that's at a very high temperature. As we can see in this diagram, we have a source at temperature TH. It's called a source because the working substance, which is here in the engine, the working substance is in Carnot's engine is actually an ideal gas. And the working substance is able to draw heat from the source or absorb heat from the source, convert a part of it into work, and reject the remaining heat to the sink. Now, the sink is a cold object at temperature Tc here. And so you can see that QH is the heat absorbed from the source, QC is the heat rejected to the sink, and the work done by the working substance is the difference between them. So the work is QH minus QC. So once again, the Carnot's engine must have three parts: the source, which is able to give any amount of heat to the working substance; the sink, which is able to absorb any amount of heat; and the working substance, which is an ideal gas in the Carnot's engine. So the heat absorbed from the source is QH, H for hot. The temperature of the source is TH. The heat rejected to the sink is QC, and the temperature of the sink is TC. And all temperatures have to be in Kelvin. Therefore, the work done is QH minus QC, and the efficiency of the engine is the work done divided by the heat absorbed from the source. So the efficiency is W over QH, which can also be written as QH minus QC by QH, or 1 minus QC by QH. Efficiency can also be represented in terms of the temperatures. And it's a similar formula, except that QH is replaced by TH and QC by TC. So we have efficiency is TH minus TC by TH, or 1 minus TC by TH. The maximum efficiency of an ideal engine is 100%, or 1. Now, when does that happen? The efficiency becomes 1 only if TC becomes 0. This is the concept that led to the formation of the Kelvin scale, where we say that the minimum temperature that can be reached is absolute 0. And we're sure that there can be no negative temperatures, because if there is a negative TC, two negatives make a positive, and the efficiency would become more than 1, which is impossible. So Kelvin scale is also called a thermodynamic scale of temperature because it's based on this idea. The diagram here represents the Carnot cycle. Carnot cycle consists of 4 processes: Mn, No, Op, and Pm. Mn. Let's look at each one of the processes. Since this is a pressure volume diagram, it's very clear that Mn is an expansion because the volume is increasing from M to N while the pressure is decreasing. In fact, it's an isothermal expansion. That means it takes place at a constant temperature, which is the temperature of the source, that is TH. So Mn is an isothermal expansion where the working substance absorbs QH amount of heat at a constant temperature TH. NO. NO is an adiabatic expansion or an isentropic expansion where there's no heat flow into the working substance or out of it. That's why it's adiabatic, but it's an expansion. So NO is an adiabatic expansion. And then when we look at OP, it's a compression. Now this is an isothermal compression where QC amount of heat is rejected to the sink at a constant temperature TC, which is the temperature of the sink. And then finally, we have PM, which is an adiabatic compression. Adiabatic compression. And this is called the Carnot's cycle. The useful work done in Carnot cycle is given by the area of M and OP. And that means if the area of the Carnot cycle is bigger, then there is more useful work done. Now, when we transition to a gasoline engine, it's an internal combustion engine. That means the working substance absorbs heat inside the engine, unlike a steam engine, which is an external combustion engine. All right, so the engine is actually a cylinder, as you can see here. It's a cylinder fitted with a piston, and the piston is able to move back and forth. There are two valves. One is an inlet valve, the other is an exhaust valve. There is also a spark plug here that can produce sparks electrically. And the gasoline engine is a four-stroke engine. Although you could make it work as a two-stroke engine, it's basically a four-stroke engine. And I'm going to explain the working of the gasoline engine. But before that, we should know that the source, which is the place from where the working substance absorbs heat, is the engine. So the source is the engine. The sink where the heat is rejected is the atmosphere, because heat is rejected to the atmosphere. And what is the working substance? Many people think that the working substance is gasoline, but that's not right. Air is the working substance. Gasoline is the fuel that burns and gives heat to the air inside the engine. So the working substance is air. Once again, the source is the engine, the sink is the atmosphere, the working substance is air, and the fuel used is gasoline, which supplies heat to the air. So now let's look at the working, the processes involved. The first process is called the suction stroke. The word suction means the inlet valve opens and a mixture of air and gasoline vapor is pulled into the cylinder as the piston goes or moves backwards. So in this case, since the inlet valve is open, the pressure is constant at atmospheric pressure or 1 atm. So that's what this graph represents. So you see that the volume increases because the piston moves outwards and sucks the air gasoline mixture into the cylinder, but the pressure is constant at 1 atm. This is the suction stroke and is represented by AB on the pressure volume indicator diagram. In the next process, the piston starts moving back up again. Now the inlet valve is closed, as also is the exhaust valve. So both valves are closed. And as the piston moves up, the volume decreases while the pressure increases. So definitely this is a compression. This is an adiabatic compression. And the temperature goes up actually because the sudden compression of a gas leads to increase in temperature. So that's represented by BC. It's an adiabatic compression. At the end of the compression, which is CD, the compression is BC. BC is the adiabatic compression. Right at the end of the adiabatic compression, the spark plug produces sparks. And when sparks are produced, gasoline burns and air absorbs heat. Now this is called the ignition. So first we had the suction stroke, then we have the compression and the ignition together called the compression stroke. The compression stroke. And now at the end of compression, the pressure inside is so high that the piston flies outwards. The piston flies outwards. That is represented by DE. This is called the power stroke. So this is the stroke where the engine really gets power from the explosion inside as the air pushes the piston back out. That's the power stroke. And right at the end of the power stroke, the exhaust valve V2 opens. When the valve V2 opens, as you can see here, when the valve V2 opens, the pressure inside reduces to the atmospheric pressure. So the pressure drops down at constant volume. Notice that at ignition and during this valve exhaust, the volume is constant, both cases. And so now the pressure is decreased to atmospheric pressure. And finally, as the piston moves back in again, it pushes the burnt gases outside. Just pushes all of it out. That's called the exhaust stroke. So there are the 4 strokes in a gasoline engine designed by the German engineer Otto. It's called the Otto cycle, OTTO. And what are the strokes again? Suction stroke, compression and ignition, together called the compression stroke, the power stroke, where the engine actually gets power, and the valve exhaust and the exhaust stroke, together called the exhaust stroke. So ignition stroke, compression stroke, power stroke, and exhaust stroke. These are the 4 strokes in a gasoline engine. The efficiency of the gasoline engine is given by this formula: 1 minus 1 by V1 by V2 whole raised to gamma minus 1. Now, V1 is the volume at this point. Theoretically, the volume could be 0, but practically, it's not 0. The piston cannot move all the way back up. So there'll be a small volume, right? So that's the volume V1. And then the volume at this point is V2. So V1, okay, so I got it backwards. This V1 is the volume here, and V2 is the volume at this point. So we have V1 by V2 raised to gamma minus 1. Gamma is the ratio of specific heats. It's a Cp by Cv, where Cp is the specific heat at constant pressure. Cv is the specific heat at constant volume. I'm going to talk about all this in another video. Right for now, you need to know that for air, gamma has a value 1.4. So if we substitute the value of gamma and assume that V1 by V2 is 10, because usually it's about 9 to 10. This ratio, V1 by V2. Let's take it as 10 and calculate the efficiency. Now for V1 by V2 is equal to 10 and gamma is equal to 1.4. Oh, we get the efficiency as 60%. That should be efficiency right there, 60%, not gamma. So that's the working of the gasoline engine. And thank you for watching. We'll see you on the next video.